Hi, good evening. It's Tuesday, March 24, and what I'm recording here is a talk through of my slides, which I normally give during week 10 of the course. I call it meeting 9 because I don't give slides during my midterm. And the, the topic for this set is Fourier, Fourier's theorem, Fourier series. The take-home message of this is going to be that any waveform that repeats can be made up of simple sine waves. So we spent some time doing labs earlier in the class, so the massive spring and the pendulum and so on, the simple harmonic motion labs, and played with tuning forks in one of the labs too. And there we deal with patterns that obey basically sine wave functions. Right? Turns out any repeating tone can be expressed in terms of sine waves or cosine waves or some combination of these. All right. I'm going to go to my Chrome window showing how I do week 10 content. Now this brief lecture will go up here eventually, but I already spent earlier today some time this morning and early afternoon making videos just featuring the applets that I usually show off in this class. One is by Falstad. He has his own domain, and it's a really good way of looking at different Fourier recipes because different wave patterns, things like sawtooth, square, triangle, all these, right, have recipes of sine waves that go in them. And there's another applet which is one put on by the FET team, and this I have less luck showing off to people nowadays because it's a legacy app and I can only get it to run on my ancient laptop. I did screen capture a couple of minutes of me playing with that applet there, and one of the homework questions I ask actually asks about exactly this situation you can see in the thumbnail. Um, what happens if you take all the harmonics of a wave and add them together equally? So that's worth a brief watch as well. Right. Really, a lot of my class is playing around with those, and I've already put in the work to record those. So I'm not going to spend the time going through those explanations now. I'm just going to go through what I have for for slides that can't be covered by one of those two. There is, as of just a year or two ago, a video about the Fourier transform, and math involving Fourier stuff can start looking intimidating really quickly. Even if you look up simple Wikipedia articles about it, you're already seeing integrals and exponentials of complex numbers and stuff. But really, when you have an exponential with complex number in it, it's really made up of sines and cosines. So there's a link between sines and cosines, which I think you are a little more familiar with, and these functions that we're talking about. So this this video is available, but you can play with an applet here and see a video of me also narrating a bit of that. All right, so that's where a lot of the work for this comes in. So like understanding all the recipes that I'm talking about is best seen there, and you can even watch those first before going into all this. Now, for here, right, I have 26 slides, but some of them are just links to these applets I'm talking about, and I will only summarize here. Okay. Now, for my class, may also have you remotely do a decibel meter lab. It turns out just every phone platform has apps you can get for free, so you can do this in a number of places. I've often done a quiz the following week, but I haven't set that up yet. And I also linked to that video. I put it directly on my Canvas, but you can optionally view those if you're curious later. Now, in the past couple of classes, right, just before our interruption, I gave a lecture about frequency and pitch, about different systems of temperament, and the first one that I actually did record is about intensity in the decibel system. So it's a way of formalizing, it's a way of formalizing what intensity is. Not exactly the same thing as loudness, but the dB scale is something that's very meaningful to us acoustics people. Now, what we'll look at a little bit here is timbre, so tonal quality. You can blindfolded, right? I can play you an A on a guitar and a violin and sing one, play it on a wind instrument, something like this. And blindfolded, you'd be able to tell which is which. But they're playing the same fundamental frequency, so what's going on? It turns out those are all complex waves you're getting from those instruments, and they have different components to them. So today we'll talk a little bit about what kind of thing those components are. Something like a tuning fork emits a sine wave shaped pattern. Simple harmonic motion, again, goes along with some of the first labs that we did in the class. All right. But for most instruments, you get overtones or higher frequency parts mixed in, and these are harmonics of the fundamental. So this should say if a string, that, okay. If you use capital A, like an A string is, that could be 220 hertz or 110 or something like this. But I mean, the point is, if you have a string playing 200 hertz, that's not really an in-tune note on the piano at all. If you're playing 200 hertz on a piano or on a guitar string or something like this, you're not going to hear just 200. You're going to hear 200, 400, 600, 800, and all of those. And so on a string, you're going to hear all of the harmonics. Different instruments, depending on their construction, may only have some of these, but the point is all of them will have a series of those and their own mix to it. Okay. So each sine wave that makes up a complex tone is called a partial. You have the fundamental, and the overtones are the higher bits. All right. And most of the overtones correspond to real notes if your fundamental is supposed to be playing an actual note. So I guess the point is the overtones you get aren't just random gibberish. They'll often be related to the fundamental you're trying to play. And a quick example is, let's say A220 is being played somewhere. So you have a string playing A220. You're not getting just A. You're getting 440. That's also an A. You're getting 660. And that is an E. All right. The way you know it's an E is that 440 and 660 are in a 2-to-3 ratio, and that's a perfect fifth, and an E is a fifth above A. So A, B, C sharp, D, E. Yeah, E is the fifth. And so E is 660 hertz roughly. Now, this wouldn't be an E under standard 12-tone equal temperament, and this is like a just interval, but I mean, it's legit. You play that and it's an E. Now, the 880 is another octave up. That's twice 440, so that's an A again. The fifth harmonic is 1100, and that is C sharp. That's a major third, because why is that moving? That's strange. Go back. All right. If you have two frequencies in a 5-to-4 ratio, you might remember if your class covered this. I covered it in a lecture, not a video, but 5-to-4 is a just interval of a major third. Remember in Pythagorean temperament, the major third was 81/64, but those fractions are messy. So if you flatten it a little to 80/64, that reduces to 5/4. And so, right, this harmonic is a major third up, which is C sharp. Then the sixth harmonic is double the third harmonic, so it's the same note, an octave up, so it's an E. And I don't have it written here, but the seventh one in the series is a minor seventh in this scale. So in the A major scale, the minor seven is a G natural, right? So the seventh harmonic is a G natural. The eighth harmonic is an A again, because it's double It's double the fourth harmonic. And the ninth harmonic would be a B, because we use 9:8 ratios to define whole steps in some ways of looking at temperament, like Pythagorean and just temperament both use 9/8. So all of these notes, these notes are the ones that make up what's called the harmonic series. And it's not like if I play A on a guitar string, you'll do that, right? You're hearing, an explicit chord with all of those in there. The higher harmonics are at a much, much, much lower level, but they're in there, and they make up the timbre of the instrument, and the different mixes of these higher harmonics makes up and helps define, what is being played. So when you hear about a harmonic series, it's like this, okay, root, then an octave, then a fifth, then another octave, then a third, then a fifth, minor seventh, octave, major second, right? Those are the intervals that you get when you take the harmonics. And the applets that I do videos on let you control the relative sizes of these harmonics with each other. Now, when you mix these all together, each harmonic could be different phases. So some of them we may make 180 degrees out of phase. They won't cause any canceling or any total cancellation because they're different frequencies and different amplitudes. But you will often see me in the applets giving like a negative value to the recipe. It's like, I care what the amplitude is, but I also want it to be flipped upside down. So shifted phases do play a role. I'll make that pretty clear right now. Within the last month or so, right? Within the last month or so, I saw a really cool animation over Twitter. Here it is. Okay. So this is one way of showing where a sawtooth wave comes from. And in the various colors, you see all the harmonics, and you notice from front to back, the frequencies go up, but the amplitudes also go down, right? You can maybe tell just looking at the first two, right? This purpley wave has half the wavelength, twice the frequency of this more red-looking thing. But you can see as they all shift phases with respect to each other, the sum total, which is this white thing, right, shifts. And at one moment like there, and one moment like there, right, you get two different saws, one going, down to up, the other going up to down, depending on how they all line up with each other. So we can always shift the phases of these things. And then there are intermediate cases where you get more like spikes. You don't get a saw wave at all, really. So how you phase shift the pieces matters a little bit for what your final waveform is going to be. I thought that was a cool visualization, and I when did they put that was posted March 5th, 2020, so just a couple weeks ago, and I put it on my canvas just to remind myself. I figured now I'm showing off everything on the computer, so I might as well share that with you. Okay, so back to these. Now this is normally where, say, it's applet time. So I've made available to all the instructors of the class. Am I going through that applet? I know Professor Nasser shows the same one. Right. I say this FET one may be better, and it's not as accessible. Like Macs just don't like it, so that's why I needed to do a voiceover a different way. But yeah, I definitely encourage, if you can click on this and go to it and just play around with some of the settings. You can do that even before I walk you through it in a different video. All right, so Fourier's theorem states that any waveform that repeats in time can be constructed by adding up a bunch of sine waves or cosine waves, and those applets, my videos on them show how it does it. Actually, Fourier wasn't studying anything about acoustics at all when coming up with this. He was studying a problem with heat, and um, there was a tricky equation. It wasn't really that easily solvable, but they, back then they knew how to solve it if there was a sine in there somewhere. The heat source was obeyed some kind of sine wave pattern. So then he thought, well, what if I could make everything into a combination of sine waves? And so here we are, right? There's a lot of areas where this comes in. It's used in acoustics, electrical engineering, signal processing of all kinds, images, digital signal processing, heat problems, right? I'm going to talk mostly in the context how it's useful for us, right? And you can do a Fourier transform, which takes in an input wave and it breaks it down into which pieces it is. I think the 3 blue 1 brown video I linked to does a particularly good job showing that off. You can take a major chord and play it, and if you take that input signal and you do this math on it, it will tell you how much of each of the notes are in there. Okay, so please go to my other videos where I show how these go. A summary of what that says is, if you want to make a sawtooth wave, right, you turn your fundamental frequency to whatever amplitude you want, and then you add the harmonics, but don't add them to the same amplitude. The second harmonic, make it half. The third, you make it 1/3 the amplitude. The fourth one, you make it 1/4 of the amplitude. I suggest here to flip the even numbered ones upside down, so shift their phases 180 degrees. That makes one kind of sawtooth wave. When I go through this in my class and I forget to flip the even numbered ones upside down, you still get a sawtooth wave. It just goes the other way. Instead of going like, it goes like this. One of those two. Okay. The square wave has the same pieces, except the even ones are out. So like if you were making a 220 hertz square wave, it would not have any pieces at all that are, second harmonic 440, fourth harmonic 880, yeah, so on. Yes, so the even number ones are out. The triangle wave also only uses the odd harmonics, but instead of the third harmonic being 1/3 the amplitude, it's actually 1/9 the amplitude of the fundamental. And the fifth harmonic, right, in the square wave, you make the fifth harmonic 1/5 the amplitude. To make the triangle wave, you make it 1/25 the amplitude. So for the triangle wave, what you find is that the extra overtones that you're adding, the amplitudes, you make them really, really small. In my videos I post elsewhere, the triangle sounds the closest to a sine tone, and that's for good reason. We're not adding much of these overtones in. In my Falstad video, I also talk about even and odd functions a bit. So just looking at the symmetry, the sine function is what's called an odd function, right? So that means if you take the sine of a number, the sine of that number's opposite is exactly opposite. So like the sine of 2 is almost to this peak 1 here. The sine of -2 is almost -1. It's pretty close to that, right? The cosine function is even. It has a different kind of symmetry. Okay, the cosine of x and the cosine of -x are the same, because this function is symmetric around this axis. So in my videos, especially the Falstad one, you can basically draw any periodic function you like, and it'll tell you sines and cosines, what mix of them will make up that function. Right? But a takeaway is that if the function that you're modeling, if it's a saw or a triangle or a square or something like that, if the function you're trying to model this way is odd, then you only use sines. And if it's even, you only use cosines. And if the function is neither odd nor even, you have to use some combination of both. So the math can get kind of intimidating. I believe, I mean, this isn't exactly what's in my notes, but it's something that's very close. What a Fourier series is just this sum of cosine functions and the sum of sine functions. Right? You have this first term here, which is basically a general shift up or down. And the goal in a Fourier analysis is to determine how big these coefficients are. So for example, for a sawtooth wave, I might make a B1, B1, B2 would be a half or negative a half, B3 would be 1/3, B4 would be negative 1/4, those kind of things. When you're asked to skip a harmonic, that coefficient then would become 0. Right? And there are formulas using calculus that give the value of these coefficients individually, but the kind of things that I typically ask in the homework are to look at functions and determine which ones, like without doing any math, can you tell are 0 or not. So basically a fancy way of saying what I said on the slide here is that if a function is odd, you only use the sines, and if a function is even, you only build it up with the cosines. That means in this language, if a function is odd, then all of these a coefficients are 0. And if a function is even, all of these b coefficients are 0. I took this from a site which has some good introduction called www.thefouriertransform.com. Most places you'll look up will have something in it that looks like this. M and N here, I mean, this should be somewhat familiar stuff if you've gone through notes in previous lessons in the class. M and N just represent harmonic numbers, right? So one is for the fundamental, 2 is for the second harmonic, and so on. T is periods. We've dealt with that before. 2 pi divided by t has been called omega in many of the material we hand out when we get mathematical with our functions. So, all right. So whenever in my videos I'm manipulating those amplitudes, I'm really just manipulating or trying to learn something about what the A and B values are. If you haven't seen before, this is a capital sigma, which just means a sum. And you have to sum up from 1 to infinity, basically all the harmonics. You have to figure out how each one of them fits in. For most typical waves, the super high ones, the amplitudes aren't that big and they don't contribute a whole lot. But you do need infinitely many of them. And so when you make something like a saw or a square or a triangle out of sines, you're doing Fourier synthesis, and analysis does the reverse. When you take what's called a Fourier transform of something, right? This is the thing 3 blue 1 brown illustrates pretty well. You can take an input signal and pick out what frequencies are in it. So I like this XKCD comic, right? I took the Fourier transform of my cat. And this looks like, I mean, I don't know if you've seen many frequency spectra before, but this looks like a frequency spectrum of a musical instrument or something. They happen to draw it here like a cat, but what this graph would mean is you have particular peaks at particular frequencies. If this were something like speech or meow, those peaks would be what we call formants. And those frequencies occur at particular places. For a speaker, it has something to do with the dimensions of your vocal cord system. So, right, it's often good to know, right, where the spikes are, right? What frequencies make up a sound, and what are their relative levels? Okay. Now, I already mentioned at the start, right? We're talking about this a lot in terms of sound and music, but Fourier originally came up with it to solve heat problems. All sorts of engineering problems use this in signal processing as well. Right? You can do equalization this way. You know, if you know the frequency components of a sound, you can selectively noise gate them or change their levels, or you have powers to manipulate things that you otherwise wouldn't have. Just to show you some instruments, if you were to take a frequency spectrum of a flute playing a note, this might be what you get. On the x-axis here, we have frequency in kilohertz. And on the y-axis is a decibel scale. This is not an absolute decibel scale. I don't know what 0 dB is supposed to represent here, but what you can get is relative levels between them. So if a flute plays this G note, you actually get this spectrum, and notice there's multiple spikes. The fundamental frequency itself is the strongest one, like we expect, but you get an octave up, and then a fifth, another octave, a third, a fifth, minor 7, octave. This would be A, this spike here. But notice, or even though in this diagram, these all look fairly prominent, the fact that the y-axis is a decibel scale is kind of a big deal. So I mean, this G4 is around, I don't know, minus 33, and the D6 is around minus 35, 36. Maybe this is at 32 or so. I mean, the point is, there's about a 3 decibel difference between these two spikes. They look very close together, but in the decibel unit, you learn that 3 dB could be a lot. It's like, well, half intensity in one way of looking at it. Okay. Now, a violin playing the same note, right, it has all the same spikes. Everything in the harmonic series is there, but it's a different mix of them. So this different mix is what lets us hear this instrument is different from the other. Now, many years ago, we had a colloquium speaker here who studied acoustics and was also a good clarinet player. And clarinets have a different design. So what you saw for the flute and violin are pretty typical. You get every single harmonic, but for a clarinet, you don't get them all. So this is a clarinet playing something at about 250 hertz, but notice the 500 hertz is practically gone. The 700 hertz 50 is very, very high and spiky. The fourth harmonic is gone and the fifth harmonic is there. So clarinets only basically play the odd harmonics, and that has something to do with its construction. Clarinets are often called open-closed things because right on one end you have the reed, and the other end is the open bell. Flutes act something like they're more like they're open pipes on both ends. So when we studied pipes, you saw that closed and open pipes allow different harmonics. Pipes closed on one end only let the odd ones come out. Right. Our speaker that day said that, right, that in some cases the third harmonic may be the loudest. This would depend on what register that you're playing in, but right. Point is, you have a different spectrum there. I often play. There's a YouTube video that I play, and I was inspired to do this a few years ago. A student asked me, well, "What's a piano spectrum like?" And the answer is, it so depends, right? It's nuts how how the frequency spectrum changes. It depends on what note you play, where on the keyboard it is, and your dynamics. So even the same note played, fortissimo versus pianissimo, right? Fortissimo, you get a lot more of the harmonics prominent. Pianissimo, you only get the first couple. So it's not just that the whole level is different, but the harmonics that you get are different. And the video that I show actually shows somebody going do, 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 going up the whole keyboard, and you can see the frequency spectrum graph for each key. And as you go up, you're dealing with strings made of different material. You're dealing with pairs versus triples of strings. There are a lot of differences between the low and high notes on a piano timbre-wise. Okay, so nearly done. I'll shortly summarize the rest. I often bring up problems with aliasing in this class, and the reason is because the last few slides should be convincing that even though we think we're playing one frequency, we're often getting higher frequency parts in it. So just because you're playing, A440 on an instrument, you may be getting partials or overtones well into the thousands, right? And this is a good time to mention that if you digitally sample a signal and you don't sample it enough, there can be problems. The phenomenon in my class where we come up with this is if I take a 30 hertz standing wave and shine a 31 hertz strobe light on it, it appears to move pretty slowly. I go around the lab tables and show them this. All right. Now, many of you, if you've ever mixed audio before, you've already taken precautions to prevent aliasing, whether you know it or not. Almost everyone I ask about it knows that something called a sampling rate for audio is typically 44.1 kilohertz, and there's a reason that's chosen. So if you digitally record a signal, you're seeing where it is a certain number of times every second. That's your sampling rate. And if your sampling rate isn't high enough, you get an alias. So here's why. I made a wave here, okay? And I tried to sample it, and you can already see what happens if you connect the dots. But check out what this red wave even is in frequency. I can look at it over 10 seconds. Let's see how many periods it goes through. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 total periods in 10 seconds. And so that's 0.9 cycles per second. All right. But if my sample rate is 1, that means every time the second ticks, I see where this is. Then if you play connect the dots, you get something like this. And so the wave, as I've digitally sampled it, actually only goes through 1 cycle in 10 seconds. So the frequency I'm trying in this case to sample is 0.9 hertz, but my sample rate is 1. And so the result is an alias of 0.1 hertz. And if you notice that 0.1 is the difference between my original frequency and the sample rate, that's exactly the point I want you to get out of this. So if you want to know in general, make this a little tinier, right? If you want to know in general where an alias can happen, what your alias frequency is the frequency of your sampled original minus some multiple of the sample rate, and usually n equals 1 gives the most important results you'd have to worry about. That certainly worked here. So in my example, my alias frequency was 0.1, my sampled original was 0.9 hertz, and the sample rate was 1. The bars on the outside are absolute value bars to guarantee positive numbers, right? So that's where aliases are located. And so the reason your sample rate in audio is so high is so that you don't have audible aliases anywhere. I'll worry about that a little bit later. But yeah, here's a summary in words. That's why I kind of went out of order on my slides. The difference between the sample rate and original signal gives an alias frequency. Multiple aliases are possible, but we saw in the slides here visually where the alias comes from. And you can even see it visually with the strobe light demo, right? Visual aliases are just as possible as audio aliases. Now, where does this apply to audio? You sample typically, or we do when we record digitally, at 44.1 kilohertz. Okay. Now, by choosing that, we're observing something called the Nyquist criterion. And most times when we're recording audio digitally, you record it and then you low pass filter it to get rid of the high frequency stuff, especially above 20 kilohertz. We can throw that away because we can't hear above that, so doesn't pay to add it. So no matter what your higher frequency partials are, we say nothing above 20K. That's it, they're gone. All right. And the Nyquist criterion tells us, right, if you're recording up to 20K, if your sample rate is at least double that, you won't have any alias problems as I've described it here. So 44.1 is a little extra, right? If the sampling, if your sampling rate were lower, 30 or 30 kilohertz, let's say, then you would get audible aliases um, if you didn't filter out everything above 15, right? Because if you let through, say, like 20 kilohertz in there, if you let 20 kilohertz through in your signal and your sample rate was 30 kilohertz, then you'd get an alias that's 10K. Now, many of us in class, me included, have trouble hearing 20 kilohertz. It's about, I don't know, a half or a third of my students when I test them, all right? But if you let 20 kilohertz through and your sample rate is only 30, then the alias would be 10, and almost everyone in the room, including me, can pretty easily hear that. So, right, 44.1 is extra. I've seen some workstations go as high as 48 or 96. I mean, you can increase the sample rate and get more precise signals. That takes more, more time to process it computer-wise and more disk space to hold it and so on. So, other higher sample rates I've seen used before, but just something to worry about when you think about signals digitally. Right. So that's the end of that. I hope, I mean, really a lot of where I have fun teaching this class is going through those applets and really just mixing the waves and seeing what kind of harmonic mixes give you the patterns that I'm interested in. So um, that is where that's where a lot of the most interesting stuff here happens. And the slides are kind of dry, but I wanted to explain what I was doing and summarize, talk about aliasing a little bit, and review that, even though, so for Fourier's theorem, right, every repeating wave function or waveform can be written as a sum of sines and cosines. Even though, right, this looks crazy, if you think of, if you look at the other videos and you think of it as just finding a recipe, like finding out what numbers go in for these A's or B's, you get a little bit more of the point, at least as far as I want to show it. So checking in, yep, got one sleeping companion. It is now 6 p.m. here. Better get up soon or else it's going to keep me up at night. It'll happen anyway. All right, bye.